All right, everyone, we are going to do our problem 2, lift force. So I'm trying to describe or measure the lift force on my rectangular parallelepiped described below. This is our expression. Rho is the air density, A is the reference area, which here is length times width. V is the velocity relative to the fluid. Measure the length of the object 24 times, obtain a sample mean, etc., etc. Width of the object 3 times, density. All right, so we know we're going to have to calculate uncertainty. Now the important point is 1% significance. What dominates? And let's get at it. So let's go ahead and let's start out this problem. Now I just solved a previous problem. So again, I want to evaluate quit kernel. I'm going to just do this locally. I'm going to let it think about it. So I'm going to define my function first. Then we'll go ahead and go step by step and we'll identify source of precision error, source of bias error, and everything in between. So let's go ahead and let's wait for this to think. It's always good to have time to think. Mathematica also needs time to think. So let's go ahead. Let's take a peek. Think. There we go. All right, so let's go ahead and we're going to go open up here. So let's go ahead. I'm going to actually start with the ANOVA, but I'm also going to pull from my statistics, and I'm going to pull specifically, I want this, my t value, the quantile, student t distribution, et cetera, et cetera. So let's go ahead and let's paste this in. So my function is FL, so FList is going to be 1/2, and it's going to be equal to rho times area, which is just length times width times velocity squared. So these are essentially those values, or the expressions. Now, I'm going to do bias error first. So let's go ahead and read through the problem. Obtain this. I measured the density, measured length of object. Let's see here. Let's see what we got here. So I have the density, measure the device of the air, density of the air using a device that had a resolution of this. So milligrams per meter cubed. So to go from milligrams to kilograms, it's 10 to the minus 6, right? So let's just do 10 to the minus 6. But that's divided by millimeter, which is 10 to the minus 3 cubed. So what will that look like? So let's look at this here. So, minus 3. That could be trouble. So I just need to multiply this by 1,000. So my uncertainty in rho is equal to basically 0.001 times 1,000. Excellent. So that's my uncertainty in the density. Measure the density of air using blah. The velocity is measuring with a sensor with millimeter per second. So my uncertainty in the velocity equals 1 times 10 to the minus 3. And that's all we've got, right? Because I need meter per second. Let's see. I don't have any information about the length and the width, so I'm going to have to set that as 0. So now I'm going to say my dFL d rho equals the derivative of FL with respect to rho. I can do the same thing here for UV, not rho, dV, velocity, and now we're going to do bias. So my bias is going to be equal to square root of, and actually we can do here, we need to do dF rho times uncertainty in rho. And I remember I want this to be unitless, so I'm going to divide out by FL. And then that's going to be squared plus, and then we'll go through here. And then we can do FL, rho, and then we can say, instead of rho, we want V, and then UV. And there we go. And what we can do right now if we want to, and I would suggest to do so, let's go ahead and say nominally our rho is going to be equal to what? Grams per meter cubed. We need it kilograms, so 1,225 times 10 to the minus 3, right? And then our velocity is nominally going to be, and actually we can just define this right now, but we'll do it later. We'll do it right now. Velocity has a sample mean of 15.3. So this is going to be our bias error, quite large. So that's what we got there. Now let's go ahead and build out our precision. So our precision error, what do we have? So we told number of length measurements equals 24. We're told that x length is equal to 12.6 times 10 to the minus 3, and our s of the length is equal to 0.001 times 10 to the minus 2. The number of width measurements equals 3. And we're just doing that. L. The x of the width, so 3 times sample mean of equals 0.6 times 10 to the minus 3. And s width equals 0.001 times 10 to the minus 3. Excellent. So those are all the values that we have. So there's going to be, and there's also number of velocity measurements. I don't want to capitalize it. Number of velocity measurements equals what? 17. Number or x velocity equals 15.3, and then s velocity equals 189 times 10 to the minus 2. There we go. Fantastic. So now we have to do, we have all these values. So now our precision error in length equals, now I'm going to pull out this student t distribution. So I need this number. That's my t theoretical value. So what we're going to do is we'll put that in right here. We'll do the length. So instead of the length, I just need my number of length measurements, minus 1. And now it's going to be 1 minus, so our alpha is 0.01 because 99%, but it needs to be divided by 2. So that'll be our t value times standard deviation of length divided by square root of the number of length. So that's my t value times standard deviation divided by square root of n, and then now we're dividing that whole thing by XL. And there we go. So that's our precision error length. For width, we're just going to change W, 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 and W, and W. And then here, we're just going to change it to velocity here, V, V, V. And then now what we're going to do is we're going to do the total uncertainty. So U, FL is equal to square root of our bias squared plus our precision L squared plus our precision width squared plus our precision V squared. And that's going to be all equal to basically the same value. Bias error obviously dominates significantly. If we change the resolution of our tool, we can get much, much, much better values there. So if we change that, we can redesign the experiment. Fantastic. The way the velocity measurements use a velocity sensor, connected to DAC, built-in filtering application, 0.5 range. There's a collaboration equation used to convert the voltage values to velocity values. MATLAB code communicates with the DAC to give us an output voltage versus time values. Draw the data limits for measuring the lift force. Ooh. I may need to change this to, let's just do this for velocity. So I'm going to just say that's velocity. I'm going to have to change that in just a second. So our measure and is velocity. Our first stage is sensor transduction. So the velocity is converted to a voltage, an analogous signal. That is, like we see here, these basically filtered, amplified, plus the equation, right, that converts voltage values to velocity values. So all those three go in that second stage, the signal processing. And then the output is just your MATLAB code. Alternatively, you can also say maybe the calibration stage goes right here for calibration. But that's it. Finally, we're working with an ANOVA data set. So let's look at our ANOVA data set. I need to look at downloads here. Then what we're going to do is we're going to take, let's go ahead and let's import I'm going to import this data set. So I've got my ANOVA. I want to import the data. I'm going to remove that first value, and I want to look at the first row. So I've got a two-way ANOVA. So I want to look at, for my factor A, I have 1, 2, 3. I have 6 conditions. For factor B, I have 3 conditions. So I'm going to take my data. I'm going to remove that first row, and I'm going to say FA, and I'm going to say FB. I'm going to say FA. I'm going to say FB, and I want my post-test Tukey. I want to double check. So 5, good, degrees of freedom. 3, good here, fantastic. We can clearly see FB is not statistically significant, or B is statistically significant, excuse me. A is not. At our 1%, I think we're at 1% confidence. Let me see where we're at. Or are we not? No, we are not. So we're just doing 95% confidence interval, so 0.05. Let's look at the size of the effect. So again, as usual, we're going to take, actually we can do it up here. I'm going to look at the sum of squares for A divided by that plus the error. We'll look at the size of the effect. Very small for A. For B, we can kind of probably predict it's going to be quite large. Indeed, quite large. So B is a large effect. A is basically a null effect. We're also told for A, there are no statistically significant values. So we can pick any value to maximize basically our outcome. For B, 1 and 2 is different. 2 is different. 2 is different from 1. 2 is different from 3. So if I'm looking at these averages here, B and here, I can pick B1 or B3. So either those are statistically the same. So I have to choose B1 and B3. Fantastic. And that will maximize my outcome. Is that all we need? Size of the effect. What set of conditions will maximize the output? Good, statistically significant. What assumptions are we making? This is a good question. By doing this Tukey test, we're assuming that the variances of the variables are equal and the number of measurements are the same as well. So that is a big assumption. We might want to use Games-Hal because we're not necessarily sure that that is true, but it's good enough for an approximation. Fantastic. Thanks. We'll see you next video. Bye.